Today's lecture I will continue for a few minutes about the dual spaces. Last time we did dual spaces. I will continue for a few minutes and then we will go to quotient spaces. So, I will summarize what we did in the last lecture about dual spaces. So, I will summarize only in a finite dimensional case. So, V finite dimensional K vector space and V star, then the dual of V. This is home K V K. The elements are linear forms on V. K linear forms on V. So, they are linear maps from V to K. And what we have seen is, in this case is to study the subspaces of V and subspaces of V star on the other hand. We gave a map from this direction and also gave a map in this direction. This map was denoted by, the first map is any subspace U of V is mapped to the right circle on U, that is by definition all those linear forms which vanish on U. So, that means U is contained in the kernel of E. This is clearly a subspace of V star, and also we have proved that the relation between their, if dimension U has dimension U, then here that dimension is nothing but codimension of this. And we have seen this map is injective. Actually, we have produced the inverse in a case of finite dimension. The inverse is take any subspace W and map it to W left circle W, that is by definition all those vectors x in V such that every linear form in W vanish on this x. Ex is 0 for all E in W. This is clearly a subspace of V, and again the same dimension of W here, that is equal to codimension of codim this in V. So, actually these maps are inverses of each other. This map is denoted by somebody left circle, this map is denoted by somebody right circle, then these are inverses of each other. So, that means this composition is identity and this composition is also identity. So, in the particular case of this we had seen earlier, namely the n minus 1 dimensional subspaces of V, which are called hyperplanes, they corresponded to one dimensional subspace of V star. They are precisely generated by one linear form, one non-zero linear form. So, this is in general true, and last lecture we have seen this. How do we prove this? They are bijective. Okay, so this lecture I will continue. Just one theorem I want to prove is the following. This is the main interest of this few minutes discussion. This is the theorem. If I have a linear map F, let F belong to home KV, KVW. It is a linear map from V to W. And let me assume it is not always necessary to assume V and W finite dimensional, but let us assume V, W are finite dimensional. Then I have a dual map corresponding to F, that I am denoting by F star, and F star is a map from the other direction, W star to V star. This is F is a map from V to W. So dual map of F is a map in the other direction on the dual spaces, and by definition it is. So that means I have to define what it is on the what it is on the linear form. So if I have E here, that means E is a linear form on W. That means E is a map, K linear map from W to K, and I want to get by using this and F linear form on V. And what is best we can do is we can take F, that is from V to W, and follow it by this E. This is E. So this map is nothing but F compose E, which is now indeed an element in V star. And because E is linear, F is linear, E composite, F is also linear. So we get a map from the dual space of W to dual space of V. The arrows are changing, the directions of the arrows are changing. Now the assertion I want to prove is rank of F equal to rank of F star. So let us prove this proof. Recall that rank of F, is by definition the dimension of the image space, image of F. So I will try to imitate what we did in the proof of rank theorem. So choose a basis here. So basis here, so let W1, this is a subspace of W, W1 etc etc WR in image F be a basis, be a K basis of image of F. Okay, so these are elements in the image. So therefore certainly I can write it as W1 equal to F of V1 etc etc WR equal to F of VR, where V1 to VR are vectors in V. And because W1 to WR is a basis, we have noted that this V1 to VR are actually linearly independent, because if the linear combination is 0, apply F to that and then you will get a linear combination between F of V1 to F of VR, but F of V1 to F of VR are linearly independent because it is a basis of the image, therefore each coefficient is 0. So therefore we have proved that these V1 to VR are K linearly independent. Okay, so we can complete it to a basis, and actually the complement is nothing but the kernel. So note that V is a direct sum of the subspace generated by V1 to VR along with the kernel F. So let us call the basis of the kernel also, you extend this. So let us, I could add some, so take V1 to VR and VR plus 1 to Vn. This is the basis of kernel of F. So this is altogether it's a k basis of V. And now I have a basis of V, so I will take the dual basis corresponding to this basis of V star. So dual basis, that is V1 star, etc., etc., VR star, VR plus 1 star, etc., etc., Vn star, the dual basis of V star corresponding to the basis V1 to Vn. And we have seen that this is a basis of V star. That's a indeed. Now I want to claim that this part V1 star, VR star is a basis, is a k basis of the image F star of W star, which is image F star. That is the claim. Once I prove this claim, we are done. Then what I will get is the number of them, that is R, is also rank of F star. But this R was a rank of F. So that will finish the proof if I prove the claim. So I have to prove it's a basis. So I have to prove two things. They are linearly independent and they generate. So linearly independent is obvious because something bigger than that is a linearly independent set. So the smaller set is always independent. So clearly V1 star, VR star are linearly independent, k linearly independent. Since it is a part of a basis, it is a part of a basis. Basis is linearly independent and therefore part is linearly independent. Okay. Now what do I have to prove? I have to prove that given, so okay, first let us understand. So if E is in W star, then I know F star of E is nothing but E compose F. And we want to prove now, what do we want to prove that? We want to prove that this is a generating space. So we are proving, to prove that V1 star, VR star I made a little okay. So this one is a nothing, is a generating system for the image of image of F star, which is F star of W star, which is a subspace here of V star. So that means I want to prove that if I have anybody here in the image, it should be a combination of these V1 star up to VR star. So take anybody in the image, but just now I said anybody in the image will look like this. So if some phi belongs to the image F star, then phi must be F star of some linear form E. E is a linear form in W star, and this I know it is EF, and I want to write this phi as a linear combination of V1 star to VR star. That means I want to write this EF as elements of the a linear combination of V1 star to VR star, but EF is a linear form on V. So definitely EF has, because V1 star etc., Vn star is a basis of the dual space of V star, this definitely has a linear combination like this: AR VR star plus AR plus 1 VR plus 1 star etc., AN Vn star for some A1 to AN scalars. I am interested in proving that these guys are 0. All these coefficients after AR plus 1 etc. up to AN are 0. I want to prove that. But how do we prove that? I am going to evaluate this, both the sides, on the vectors VR plus 1 to vector Vn. So we are looking at E of EF evaluated on Vi, and I is from R plus 1 to N. Note that VR plus 1 etc. Vn, that was a basis of K, basis of the kernel of F. So this is by definition E of F of Vi, but F of Vi is 0, so this is E of 0, so this is 0, so this side is 0. On the other side it is A1 V1 star etc. plus AR VR star plus AR plus 1 VR plus 1 star plus AN Vn star, and this you want to evaluate on Vi, and what will remain? Obviously I is, we are taking from R plus 1 to N. So all these guys Vj, where j is between 1 and R, that is going to vanish here. So the first time, the only term which will survive is where Ai is coming from. So this is Ai, Vi star, Vi, which is Ai. That is the only term will survive. So you see, we have proved Ai is 0, and obviously we have used the fact that I is between R plus 1 and N. So we have checked that these coefficients are not there. So that means EF is, so therefore EF is a combination of the first R V1 star to VR star. So that proves that V1 star etc. to VR star is a basis of image of F star. So altogether we have proved very important result, which will be very useful later. Rank of F and rank of the dual are same. When I do a matrices and their ranks etc., this is the analog of the fact that a matrix and its transpose have the same rank, or in other words row rank equal to column rank etc. So now I will start a new topic, which is called quotient spaces. Before I start formally, I want to give little bit motivation and some comments. So quotient spaces in general, very important concept. This comes in every subject. For example, in the sets, we have a set X, and usually on the set there are equivalence relations. Let us call it tilde. Then we have the quotient set X by tilde. This is the set of all equivalence classes. Equivalence classes are also denoted like this. So, these are the equivalence classes of this. Because X is decomposed into the equivalence classes. This is a disjoint union. So, we are looking at the equivalence classes and collecting the different equivalence classes. Any two equivalence classes, either they are equal or they are disjoint. So, this set, quotient set, it is called the quotient set of X with respect to the relation, with respect to the equivalence relation tilde. And we have also natural map here, Q. Q is a quotient map. Any element X will go to its equivalence class. Of course, many of them will go to the same equivalence class. So, the fibers of this map are precisely the equivalence classes, and this map is surjective. So, one usually studies set with equivalence relation with this quotient map and this quotient set, because when we want to induct or for some reason you know all equivalence classes very well, then you can put the information together to get information about X. But here there is no structure on X other than it is a set. When we have now more structure on X, for example, X is a group, or X is a monoid, or X is a group, or X is a ring, or X is a vector space, then we have to worry about whether I can pass on that structure to the quotient set or not, and this is not usually the case. So, you have to give some condition on the equivalence relation, so that the structure is passed on to the quotient set. So, just to give an example, suppose when you have a group G and a subgroup H, subgroup. Now, of course, H will define the equivalence relation. Actually, H defines two equivalence relation. One is called left one and the other is called the right one. So, they are written like this, which side you write H of the tilde. And this, the first one is defined by A, B, that is if A, B inverse belong to H. And this one is X, Y if X inverse Y belong to H. I might have made some error in this, but we will cross check it. So, this equivalence relation, the equivalence classes will be the left cosets HB. So, this is the equivalence class of the first one, and this equivalence class will be the right cosets, no, left coset. This is the right coset and that is the left coset XH. In general, these two cosets are not different. So, equivalence classes are different. Now, the problem is when I take the quotient set with respect to this one, I get left cosets. So, left cosets, and with respect to this one I get left cosets. One of them I get left coset, the other I get right cosets. So, even as sets these are different, but you would like to put the group structure on this quotient set. That means you would like to define a group operation on this set, so that the quotient map becomes a group homomorphism. So, there is a quotient map here, there is also quotient map here, and we want to put a group structure here such that this quotient map is a group homomorphism. Then only it is then only it is useful, because you would like to pass on from G to this, and this does not always happen. If one analyze this, you come to a condition that H is so called a normal subgroup. This is the condition you get it, which is always true for abelian groups. Normal, you remember the normal definition is for any G in G, G H G inverse should be a subgroup of H again. This is the condition for all G. Then you call it normal. If you analyze this is the precise meaning of the fact that this equivalence relation is compatible with the group operation, or sometimes it is also called a congruence relation. So anyway, for abelian groups it's always true. So for example, we have done this construction very often for the additive group of integers. This is abelian, and we have a typical equivalence relation congruence modulo n. Congruence modulo n is a equivalence relation which is defined by A congruent to B modulo congruence modulo n if and only if the definition was B minus A divides n. And now we know what are the equivalence classes of this. Equivalence classes are precisely the residue classes, that is residue class of 0, residue class of 1 and so on, residue class of n minus 1, and this is the quotient set. This is precisely Z, this quotient set, and this is a group again under addition modulo n. So this is a group under addition modulo n. I write like this. That simply means you take integers a and b, add them usual, and take the remainder after dividing by n. So this is R, where R is uniquely determined by the division algorithm a plus b equal to q times n plus r. This r is the remainder after division by n. So this is a group again, and this group we have been calling it Z mod n. And now the natural map from here to here, Z to Z mod n, is any integer a going to its remainder after dividing by n. So that is residue class of a modulo n, and we have seen this is a group homomorphism. So this is very important when you want to pass on, when you want to do calculation modulo n, because from integers you pass on to this group and you do your calculation in this group. So in short, vector spaces also I am looking for such a thing. If I have a vector space V, I want to construct a new vector space which is like this model. So those will be called quotient spaces. This is also called quotient group of Z. It is called quotient group, or also it is called residue class group. And such a construction I want to do it for a vector space. One can do it for rings also. You can do it for almost every object. You can ask question whether given an object with some structure, if there is an equivalence relation, can we pass on to the quotient set the similar structure, or what are the conditions on the equivalence relation we may require to pass on the structure from the original set to the quotient set. Okay. So with this motivation I just want to start like I started for a group. So now let us take V to be K vector space, and let us take U to be subspace, K subspace. Then definitely this U will define an equivalence relation. U defines an equivalence relation on V. What is it? That means two vectors V and V prime. Let me call it the notation for the equivalence relation defined by U is tilde suffix U. I will fix U, so I will just write this by tilde. The definition of tilde is U V V prime in V then we say that V is related to V prime if, this is a definition, that V minus V prime belongs to U. Now let us check orally that this is indeed an equivalence relation. Remember, U is a subspace. So first is reflexivity, that is V related to V, but then V minus V is 0. All that you need to check is 0 belongs to U, but that is part of the definition of a subspace. Similarly, transitivity, V related to V prime and V prime related to say W. This means V minus V prime belongs to U. This means V prime minus W belongs to U. But if these two are in U, then their sum is also in U because it is a subspace. So that means V minus W belongs to U, and that means V is related to W. So we have checked reflexivity, transitivity, and now we want to check that it is symmetric. So symmetric means V related to V prime, V prime and V prime related to V, that should imply that. But this means V minus V prime is in U, but somebody is in U, then the minus of that is also U because it is a subspace. So V prime minus V is also in U because it is a subspace. So therefore this is also correct. So we have checked that this is an equivalence relation. And what is the quotient space now? V mod tilde is what? These are the equivalence classes. So let us see what are the equivalence classes. So for, if you fix V in V, the equivalence class of V under tilde is by definition precisely all the vectors in V which are related to this given V. So that means all these V prime such that V is related to V prime. These are the equivalence classes. For example, if V is 0, then what is the equivalence class of 0? That is precisely U. For arbitrary V, what is the equivalence class of V? That is all those vectors which I can write V plus somebody is in U, U in U. This guy is a precisely equivalence class of V, because if U is in U, then this V minus V plus U is related to V, because if I subtract V from here you get U, U is in U, and everybody is like that. So this is the notation for this I want to write it as V plus U. This is by definition, take all the vectors in U and add it to this given V. So these are visibly they are cosets of U plus in V plus. So that is a quotient set. This is nothing but cosets, that is V plus U, where V belongs to V. And we can also analyze when are the two cosets equal, that is precisely when the differences of that representatives belongs to U. And our problem is now to define a vector space structure on this quotient set, so that the natural quotient map is a k-linear map. This map should be k-linear. And this is the natural map Q, not arbitrary map. This is a map V goes to V plus U. And we want to put a structure here now. We are looking for, on this set, we are looking for addition so that it becomes abelian group. We are also looking for a scalar multiplication so that it becomes a vector space, and with this structure this Q map should be k-linear. All these things we need to check. But things are so natural that if one defines it correctly, it is clear that it is k-linear. So I will stop and we will continue after the break.